In this video, we're going to do something a little bit different. We're going to tell a biochemical story which involves free radicals. Now, we're going to talk about arachidonic acid, which I'll show you in a couple slides. But arachidonic acid is a C20 carboxylic acid, which is converted in all humans and animals into the prostaglandins. The prostaglandins, here's one example right here. But they're a group of lipid molecules which act as hormones, and they're derived, like I say, enzymatically from the arachidonic acid. Now they're vasodilators, and they affect the aggregation of blood platelets. And through their role in vasodilation, they're involved in inflammation. So if you have a inflamed ankle and you take an aspirin to reduce the inflammation, what it's doing is it's attacking the enzyme which is responsible for converting arachidonic acid into the prostaglandin, which is involved in the inflammation. So you reduce the inflammation by reducing the formation of the prostaglandins. We'll get to that in a second, but first let's review some free radical things. So here's a table of free radical stabilities, and of course this all has to do with the bond energies over here. Is a methyl up here with a very strong bond energy is very unlikely to form a radical, whereas something where you can delocalize your radical, like in the allyl system here or the benzylic system, has much lower CH bond energy, and you're much more likely to be able to do form a radical because of the delocalization. Here's allyl is 364. It's one of the lowest numbers on this table. So keeping that in mind, what we're looking for is delocalization. So applying that principle, here's a very simple question. Here I have this is a diene, and the question is well, which hydrogen is the most reactive with respect to this bromine radical? We're going to abstract a hydrogen. So how would you figure this out? Well, of course, what we want to do is we want to form the most stable radical possible, and as we just looked at a previous slide, we want an allylic position. Now B would be an allylic position because you could have delocalization here. E would be an allylic position. But look at allylic. You put a radical here, you can delocalize to the left, you can delocalize to the right. You have a 5-atom delocalization. So that looks really great. Which is the most reactive then? Of course, the one with the greatest delocalization. So very, very easy to see that that's where you'd put the radical. And essentially, you can simply draw all of these resonance structures of putting a radical on either side and totally delocalized. Very, very easy to do. Which is the strongest CH bond in arachidonic acid? Or the ones I have labeled. Which one's the least likely to form a radical? What would it be? Well, it's not D. That's the good one. So, but which of these? Well, if you look at it, methyl is the worst. And if you look at the bond energies, 421, 410, 358. So the weakest bond is the CH where you're going to form the radical. The strongest bond is the methyl, and you're not going to form a radical at the methyl. That's 100 kilojoules stronger, and it's typically not going to happen. So these are the culprits. Now there's two other positions which you could go for as well, and these would be of similar energies. It turns out the enzyme gets to choose, so the enzyme is going to choose this one, but these two here would essentially be the same energy. So again, just this delocalization, just showing you the same thing, where you can have a delocalization over 5 carbons is better than 3. So if you did C, you'd get just this delocalization. You do D, you get this delocalization. Okay, so this is the story. This is arachidonic acid. It's a C20 hydrocarbon, and our carboxylic acid, mostly hydrocarbon. It's called arachidonic acid, which I think is one of the world's best names. And there's this enzyme which is called cyclooxygenase. Actually, cyclo is misspelled. Good for me. And people abbreviate this COX, which is called COX. And you've already heard of COX inhibitors, I'm sure. And this what you're doing is you're inhibiting this process right now here. And you make this precursor, which has got these this peroxide structures. And then this precursor is converted by other enzymes into the prostaglandins. And here's one particular one. This is prostaglandin E1. So how does this work? Well, this is not how we work it, but ibuprofen and aspirin inhibit that particular enzyme, and of course this is important for reducing inflammation, and it's involved in other compounds as well, but the prostaglandins is this chief target. Okay, and so you can get relief from inflammation and pain by reducing the production of these prostaglandins. Okay, so how does this work? Well, the COX enzyme has within it this tyrosine radical. Okay, and of course there's other chemistry going on to introduce this radical into the enzyme, but you can think of the enzyme as just sitting there as a oxygen radical on the phenyl ring. It's a tyrosine from an amino acid, and this is like the resting point of the enzyme, and it's going to do this chemistry. So let's see how this works. Well, the first thing we're going to do is it's kind of like doing some of the paracyclic reactions we did before. We want to redraw the arachidonic acid in this particular conformation. I mean, there's nothing magical about this conformation other than it makes it easy to see what the chemistry is. So we're going to, first thing we're going to do is we're going to abstract the hydrogen using our tyrosine radical in the enzyme. And so which pair of hydrogens is it going to go for? Well, we've been through this. A is better than B, because A is the one that's delocalized over 5 carbons. So we're gonna grab one of those hydrogens there. We're gonna make this particular radical. Now this radical, of course, is delocalized over all these positions, and we're going to, in fact, I'm going to redraw a different radical. This is just, of course, just a resonance structure, because this is going to show you the center of reactivity. Now that radical that at the bottom of the page is going to react with nature's most common everyday radical. What is nature's most common everyday radical? This is supposed to be a clicker quiz, but can you think of what it is before I get there? Here's some pretty silly choices. Dinitrogen, is that a radical? No. Water, is water a radical? No. Is sodium chloride a radical? No. Oxygen, is it a radical? Yes, in fact, it's a diradical, right? Remember your MO diagram for dioxygen. Dioxygen has these 2 unpaired electrons on each atom, and 1 lone pair in each atom. So when you pair them up in your p orbitals, you get 3 bonding orbitals. You have two electrons left over, and they have to go into pi star. They go into pi star because it's degenerate 1 electron at a time. So it's a diradical. Now other molecules which are diradicals will do some kind of a rearrangement and form an atom-atom bond with a diradical. But oxygen is diatomic, so it can't change its shape, so it's stuck. So a diradical is stable as if it's a diatomic. Generally, diradicals are not stable because if they're on atoms other than a diatomic, the molecule will rearrange itself to pair up those electrons by forming a carbon-carbon bond. But oxygen is a diradical. We're breathing it all the time, but it's a really nasty molecule. It reacts with all kinds of things, including arachidonic acid radicals. So how do you draw the Lewis structure of a dioxygen? If you draw it this way, it's really wrong because you're implying that all the electrons are paired up. You've got 4 lone pairs. Well, it doesn't have 4 lone pairs because 2 of the electrons aren't paired. Well, you can draw it different ways. Some people draw it this way, showing that the 2 odd electrons are delocalized over both oxygen. I don't really like that. I like drawing it this way better, even though it doesn't really say anything about the double bond, but at least it's talk about the diradical nature of the molecule and forget the lone pairs. Let's just draw it this way. And what are we going to do? We're going to we're going to tack right there, and we're going to end up adding basically a peroxide to this position. So the oxygen adds on at this carbon, and then it's going to form a ring. And where it forms a ring is right up there. And this double bond has to split. 1 electron goes to form the bond to the oxygen. The other one shows up as a radical at the other carbon. And so now we have a radical there. This radical reaches across the ring into this delocalized system that we formed initially from a very initial radical, and we end up with a radical on the right-hand side there. Now that radical there is of course now the new reactive species. And what does it do? Well, it reacts with another mole of dioxygen, and it forms this radical. and that looks pretty reactive. Where is it going? It's got to do something. It wants a hydrogen really bad or another carbon. What it does, it finds the hydrogen on that tyrosine from the enzyme, from the COX enzyme, pulls off that hydrogen atom, reforming the original radical in the enzyme, return the enzyme to its original state, which is what you want to do for a catalyst, and it gives you this peroxide here, a derivative of the original arachidonic acid. And now this peroxide species is the species which goes ahead and is converted by other enzymes into the prostaglandins and through much more complicated chemistry. But this free radical beginning is a quite interesting use of radical chemistry by nature. And oxygen shows up in lots of radical reactions if you look at all kinds of biological processes. And this is a good first example. So that's the story, and I'm sticking to it.